Hey everyone. So I'm Carsten, and today I would like to talk about BBH construction by hierarchical parallel locally ordered clustering, short HBlock. This is joint work with Daniel, Josh, Rowan, John, and Andrew. Okay, let me first give you the big picture here of what this talk is about. In the end, it's all about efficiently ray tracing highly dynamic scenes. As you all know, ray tracing requires an acceleration structure over the scene, which is in almost all cases a bounding volume hierarchy. Now, with dynamic content, the scene is modified, typically on a per frame basis, and with the corresponding BVH over the scene needs to be either updated or rebuilt to accommodate these changes. In the context of real-time ray tracing, the time to update/rebuild the BVH is now on a critical path, as it takes a part of the rendering budget per frame. Also, it's worth to mention that modern real-time APIs like DXR or Vulkan support a two-level hierarchy, a top level and a bottom level acceleration structure, short TLAS or BLAS. A TLAS is essentially a BVH over instances, and a BLAS is a BVH over triangles of an object which gets instanced in the TLAS. So whenever the position of an instance changes, the TLAS BVH needs to be updated/rebuilt. If triangle changes, the corresponding BLAS BVH. So in this talk, we will mostly focus on the BLAS case, but everything presented here equally applies to the TLAS case as well. Okay, so let's assume we need to modify our BVH due to some animation happening in the scene. Now we need to decide first whether to update or rebuild the BVH. So first, let's have a brief look at the BVH update algorithm, which relies on an already existing BVH, as shown here on the left. Sorry. Now, if the position of a triangle changes, all bounding volumes enclosing the original triangle need to be updated to maintain the bounding property. This update procedure has a very low complexity, and it's therefore much faster than a full BVH rebuild. However, BVH update also has some major drawbacks. Only if the motion of the triangle is spatially limited will the enlargement of the bounding volumes up to the root node be tolerable. If that's not the case, the BVH quality will degenerate very quickly, as bounding volumes will get so large that they will overlap excessively. The overlap will reduce culling efficiency and therefore reduce ray tracing performance during rendering. So the question is, how bad can this BVH quality degeneration be? Let me quickly show you an example with some large triangle motions. So before the triangles get modified in the scene, the BVH update, which is done per frame, requires roughly half a millisecond, and the render time is about 6.5 milliseconds. So when I start the animation and the thing crumbles down to the floor, right, you can probably see that the render time in the top right corner goes up to hundreds of milliseconds, and that's basically intolerable, right? So as a consequence, if we have really unconstrained motion, we need to rebuild the BVH per frame, and there's no way around it. Okay, as we have established that we need to rebuild the BVH per frame, let's have a brief look on what BVH build methods have been proposed before. Essentially, there has been decades of work on building BVHs. So for everyone interested, I refer you to the latest STAR report, which covers all of them in more detail. As our focus is on high-quality GPU-based BVH build algorithms, we will compare HBlock against the following state-of-the-art methods. First, linear BVH, or short LBVH. This method does very little, as it essentially relies on just computing and sorting Morton codes to order primitives along a space-filling curve. The ordering creates an implicit tree hierarchy, which is then used to generate the final BVH. This has the lowest complexity and therefore the fastest build times, but it also produces the lowest BVH quality among all the different approaches. And we will use this method as a speed of light reference in terms of BVH construction times. Don't go. Okay, there we go. On the other side, PR BVH, which stands for parallel reinsertion BVH, produces the highest quality, but also has the longest build times, making it more suitable for offline and real-time construction. We will use it as a speed of light reference in terms of BVH quality. The other two, ATR BVH and Block++, produce better quality BVHs than LBVH, but also do much more work, so they are quite a bit slower than LBVH. However, LBVH, ATR BVH, Block++ are kind of the state of the art in terms of real-time GPU BVH construction, and we will compare against those. Okay, now I would like to switch gears and show you how modern GPU BVH builders like ATR BVH, block++ are conceptually structured. So an interesting observation is that modern builders can be broken down into individual phases. And most of these phases are identical across the different approaches. So let's have a quick look at those. So we typically start with a zoo of triangles. And the very first phase is kind of optional, but for ray tracing hardware architectures which support triangle pairs / quads, it makes sense to search for these pairs at the very beginning of the pipeline to reduce the number of primitives during the later phases. So once that is done, we compute an X-line bounding box, short ABB for each primitive. Based on the ABB, we compute the centroid, and then its Morton code, right? Then we sort all the Morton codes, which basically orders the primitives along a space-filling curve. That sorted list of Morton codes is the input for the binary BVH construction phase, and the binary BVH is the input for the last phase, which converts the binary BVH into a hardware-specific layout. The exact layout depends obviously on the underlying ray tracing hardware, but almost all known hardware implementation use some variant of an n-wide BVH. In our example here, it would be a 4-wide BVH. The important point is that all different BVH construction methods, including H-block, build binary BVHs, and therefore only affect the binary BVH construction phase. And for the rest of the talk, I'll focus on two major contributions that affect the last two phases. First, the fast binary BVH construction with H-block, and second, the efficient binary to n-wide BVH conversion. So let's dive right into it. As I mentioned before, we start with a sorted list of Morton codes which define an implicit LBVH tree as shown in this example. Blue are the sorted Morton codes, gray are the LBVH leaf nodes, and orange are the inner LBVH nodes. For each inner LBVH node, the Morton codes allow us to define a continuous range of leaf nodes that the corresponding subtree covers. So for example here, inner node 1, the orange one, covers leaves 0 to 3. Now when we go up the tree, the ranges get extended either to the left or to the right. So H-block will build a binary in a bottom-up fashion. So we're going to start from the leaf nodes. The basic idea will be to propagate lists of subtree root nodes up to the LBVH tree. And we therefore create such a list per leaf node, and initially it will just contain the leaf node itself. Now we traverse the implicit LBVH bottom up and extend the list as we go. So here's an example. At inner LBVH node 1, we know that the range covers the leaves 0 to 3, so we have 4 leaves in our current list of subtree root nodes. Now, at each inner LBVH node, when we go up the tree, we compare the number of entries in the list against the so-called merging threshold, which in our example here is set to 2. Whenever the list is larger than the merging threshold, we invoke a merging operation, which will reduce the number of entries in the list. This merging operation is nothing more than finding a nearest neighbor pair, right? Taking the area of the bounding boxes into account. And this is known from other PLOC-based approaches. In our example, we look at our 4 entries for a good nearest neighbor pair. And let's assume that would be leaf nodes 0 and 1. We merge the two, and this produces a new purple-colored inner node 0 on the right, which connects the 2 leaf nodes. The right side will illustrate the binary BVH that we built with H-block. Okay, so this iterative merging process continues, and we pair purple inner node 0 with leaf node 2 to create purple node 1. Now our list contains just 2 entries, and this is below the threshold, which means the merging process stops, and the current list is assigned back to the LBVH inner node 1. Right? Same procedure is applied when reaching LBVH inner node 6 here. Again, the number of entries is larger than the threshold, and we invoke the merging operation. And the reduced list is assigned back to LBVH inner node 6. Note that the entire process of bottom-up traversal and merging is done fully in parallel and not serial or sequentially as I illustrated it here. The bottom-up LBVH traversal continues, right? At any given LBVH node, we simply concatenate the lists of the left and right child nodes. For example, at inner node 4 here, our concatenated list contains leaf node 4 coming from its left child, and leaf node 5 and the purple node 2 coming from its right child. Again, the concatenated lists are larger than the threshold, so node merging is applied, and this creates purple node 3. And the reduced list is assigned back to to LBVH inner node 4. Okay, this process continues, and at LBVH root node, right, when we really reach the root node, our list contains now 4 entries: purple node 1, leaf 3 and 5, and purple node 3. Now, because we are at the root node, we continue the iterative merging process here until we have only a single entry left in the list, which will be the root node of our final binary BVH. This is the purple node 6 here. And that's the entire H-block BVH construction algorithm, which is really simple. Again, the basic idea is to use the implicit LBVH hierarchy to collect and propagate lists of subtree root nodes up the tree. If a list gets too large, we apply merging, which builds the actual binary BVH. And this one will be quite different than the original LBVH hierarchy. Note that in our implementation, we use a merging threshold of half the warp size, as everything is kind of optimized with warp processing in mind. And the nice thing is that the entire process of propagating and merging nodes can be done within just a single GPU kernel launch. Okay, so let's move on and let's focus on the last phase, the binary to n-byte BVH conversion. Previously, different approaches have been proposed to convert a binary to an n-byte BVH in a surface area heuristic optimal manner on the GPU. For example, either by performing iterative top-down approaches or by a combination of bottom-up and top-down phases, right? The important point is that all previous approaches required multiple kernel launches, while our method will do everything within a single kernel launch. So in order to achieve this, we modified the top-down approach originally proposed by Volderdal. This approach traverses the binary BVH in a top-down manner, always opening the binary node with the largest area to gather enough nodes to create an n-byte node. The issue with this kind of conceptually recursive approach is to efficiently distribute the binary node opening and the n-byte node creation across the entire GPU to maximize parallelism and efficiency. So our method solves this work distribution problem by maintaining an additional array which is sized according to the number of leaf nodes in the binary tree. This array will be used for scheduling work across GPU threads. Now we start the GPU conversion kernel with the same number of threads as we have entries in the work distribution array. The important point is that each GPU thread continuously checks whether its corresponding array slot contains a valid work assignment. At the beginning, only the binary BVH root node is placed in the first array slot, and therefore only the very first GPU thread picks up the work. Now, the very first thread starts a top-down descent. It opens the root node 8, replaces it with its children 4 and 7. Now let's assume node 7 has the largest area, so we open this node. Replaces with its children 5 and 6. Now assume 6 has the largest area, so we open it and replace it by node 0 and 1.
Carsten?
Yeah?
Should there be an animation on the slide?
Okay, let me go back. Let's move on. That's fine. Okay. Yeah, something happened. Don't worry about it. So at this point, we gathered 4 nodes, as illustrated here in gray, right? And we can create a 4 white node, which can get dumped out to memory. We can continue this opening process by putting the binary nodes that have been used to create the 4 white node to the work distribution array. The first thread continues with 1 of the 4 binary nodes, while the other 3 nodes will be picked up by threads 1 to 3. So we have 4 threads that open up the binary BVH in parallel. Okay, that process continues. Here the first thread will open up inner node 0 and replace it by its 2 children, which are actually leaf nodes. Leaf nodes cannot obviously be opened, so threads assigned leaf nodes will stop the opening process and create BVH leaf data instead. Now thread 1 opens inner node 1 and replaces it by its 2 leaf node children, and thread 3 opens up node 5, right? And this whoops, now I've lost. Okay, now the process continues until the work distribution array only contains leaf nodes. At this point, all the work has been done and the GPU kernel finishes, and that's it. So in general, letting the GPU threads continuously poll for work allows for very efficiently distributing the irregular top-down node opening across the entire GPU. Okay, let's look at some results. Quick note on the hardware-software setup. We use an AMD Radeon 7900 XT, coded up everything in HIP, right, and run it on Ubuntu Linux. So from the competitor approaches, we ported the original CUDA sources to HIP, which is quite easy, right, and put everything into a single code base to allow for a good apples-to-apples comparison. Our target hardware BBH layout is a 4-byte BBH. We use 64-bit Morton codes, which means the integer and the code is all combined in a 64-bit integer. And for performance evaluation, we use a simple diffuse path tracer. Okay, let's start with absolute times just for the binary BBH construction phase. Okay, that works. We have here 6 example scenes with varying complexity and compare HBlock against ATR BBH, Block++, and LBBH. I left out PR BBH here because the construction time for PR BBH is more measured in seconds than milliseconds, so it doesn't make really much sense here. And you can see in this chart that HBlock achieves significantly lower construction times than ATR BBH and Block++, but is a bit slower than the simple LBBH construction. Here's the same data, just visualized differently. Here it's normalized to the HBlock construction times. The bars essentially show speed-up factor of HBlock versus the other approaches. So for example, HBlock is roughly 10x faster than ATR BBH and 1.6 to 4.4x faster than Block++. And it comes within a 2x versus LBBH, which again is the speed of light reference in terms of BBH construction. Okay, now let's look at the absolute BBH4 construction times, which means the timings include all the phases. Now the difference between HBlock and the competing approaches is smaller, as the impact of the faster binary BBH construction is reduced by the cost of the other phases. The other phases have basically identical runtime costs across all the different methods. Still, HBlock significantly outperforms ATR BBH and Block++, and is just slightly slower than LBBH. Construction times are just one side of the story, right? Equally important is BBH quality. This chart compares SIH quality of the final BBH4 when you use different approaches to build the intermediate binary BBH. Everything here is normalized to the SIH when building the intermediate binary BBH with PR BBH. The higher the bar, the worse the quality. For example, for the sponsor scene, building the intermediate binary BBH with LBBH results in a 1.33x worse SIH for the final BBH compared to PR BBH. In general, LBBH produces the worst BBH4 quality, while HBlock roughly provides similar quality than ATR BBH and Block++. BBH4 SIH is a good quality measure, but what really counts in the end is ray tracing performance. So this graph here shows relative path tracing runtime performance versus a PR BBH-based construction on the y-axis and relative BBH4 build performance versus LBBH on the x-axis. So let me explain. So PR BBH on the top left produces the highest quality BBH4 and therefore achieves the highest path tracing performance. But it's more than 100x slower than LBBH in terms of BBH4 construction. LBBH on the far right achieves the highest build performance, for example measured in million triangles per second, but has the lowest quality and therefore the lowest path tracing performance. So where we want to be in this chart is the top right corner. HBlock does a big step in this direction and it achieves similar path tracing performance than ATR BBH and Block++, so it maintains the level on the y-axis while getting roughly within 50% of the LBBH build performance. So this is also an interesting chart, as it shows for an HBlock-based BBH4 construction the time spent in the different phases. And we see that finding triangle pairs, binary BBH construction, and the conversion are the most expensive phases. Interestingly, binary BBH construction got so fast by using HBlock that it's no longer the primary bottleneck of the entire build. Instead, the top-down conversion, even with our optimized work distribution, is becoming the primary bottleneck of the entire BBH4 build process. And this is mostly due to the fact that the last phase is the most memory bandwidth intensive phase, and the encoding to the hardware BBH layout is also costly. So all previous results were about BLAS construction, so here's a chart about TLAS construction, where we built a BBH4 over randomly placed instances. We compare HBlock against LBBH again with an increasing number of instances. Absolute timings are on the left, and relative overhead versus LBBH on the right. And again, HBlock, it comes within 15% of the LBVH build times and allows to build a high quality BVH for roughly 450,000 instances in just a single millisecond, which is pretty cool. Yeah? Okay, thank you. So rebuilding static scenes is kind of boring. So let's look at what HBlock and the fast conversion can do for fully dynamic scenes. So this is the scene from the beginning. It's 1.3 million triangles. Does it work? Yeah. And you can see that we can build the entire BVH4 in just 1.6 milliseconds, right? And the BVH rendering time stays constant between 8 and 10 milliseconds. So it is a larger scene, 2.5 million triangles, and we can build the entire BVH4 under just 3.2 milliseconds. And don't try to use BVH update on this scene, then the rendering time is more measured in seconds than milliseconds. Okay, so in conclusion, HBlock provides us very efficient, high-quality binary BVH conversion, right? And together with the efficient binary to n-byte BVH conversion, we have really powerful BVH construction methods and tools at our disposal. Again, HBlock is just 15% slower than LBVH, while it provides a way better quality. So the question is, why use LBVH at all? And personally, I think the biggest advantage of HBlock is its simplicity. It's just 250 lines of code for the binary BVH construction. And for all of you who ever try to implement a GPU BVH builder, that is nothing. Okay, so what will it give us? In the end, HBlock and the conversion will provide us with a higher number of dynamic primitives per frame without compromising on the BVH build time and quality. And we really hope that this will initiate a push for putting much more dynamic content in real-time ray-traced games and applications. Okay, and that's it. Thank you for listening. And,
we have some questions?
Hey, Alex.
Are there any situations as you approach when update still makes sense?
Okay, the question is whether BVH update still makes sense. Sure, absolutely. So if you have, if the motion is very limited spatially, right? If the leaves, for example, of a tree just moving a little bit, then it makes totally sense to use BVH update because it is way faster than a full BVH rebuild. But as soon as, let's say, all the branches go like this, right, then the quality will degenerate very quickly and it makes sense to do a full BVH rebuild.
I'll ask a question that may not be surprising coming from my background, but you have a very interesting GPU implementation with a lovely polling structure for the threads. How would this work in a hardware implementation?
So in general, let me go back to this chart, this here. So in general, hardware implementations are definitely possible. The question is whether it makes sense. And what I mean with that, if you look at this chart, the cost distribution is pretty much distributed over the 3 different phases, right, and a little bit for the other phases, right? So let's assume you would have a magic HBlock hardware builder, and this would reduce the cost of the orange part to 0, right? This will give you a 20–30% speed up, something like that, right? And you don't build hardware for a 20 to 30% speed up, right?
It might be fun still.
Sure. So yeah, I don't think it is possible, but whether it makes sense, I would be skeptical.
Another question?
There's one on the right.
I see on this slide that the drawing conversion is quite expensive. Why is that, and can you improve it?
So the question is why the triangle pair phase is expensive. So essentially, you have to iterate over all your meshes in the scene and find your triangle pairs. And this is we do it on a warp granularity. So we look for pairs within a warp, and you have to go over all of the index meshes. And when you store them out, you need to kind of build prefix sums on the fly. So there's additional cost kind of involved, right? And this makes the phase a little bit more costly than usual, if this makes sense.
Great. Why don't we stay on time and thank our speaker again. Thank you very much. I'll invite our next speaker up on stage.